Yeah, so last time I forgot to thank the organizers for this lovely conference, for inviting me to work very hard on 3 lectures. Free beers. Is that a promise? That's good. And so yesterday I told you why I don't think there's a layer of water at the surface of ice. And today I will try to substantiate that and look at what consequences that has for our understanding of friction on ice, also known as ice skating. And if you go to a friction conference, everybody says this friction is very important because it's responsible for an estimated between 20 and 25% of the world energy consumption. It's really true. And then they all show this this lovely drawing of how a statue of an Egyptian pharaoh called Jehuti-Hotep is dragged through the desert on a sledge. And if you go to a lubrication conference, there's always one guy that says, hey, the Egyptians already knew how to lubricate. And we know that these jars are uniquely used for water. So it was not olive oil or animal fat or whatever some people thought. And water on the sand is not making a lubrication layer, but is simply making the sand harder as in a sandcastle, and then it becomes easier to drag. And that will be important in what follows. So this is again not a lubrication problem, although there's water involved. And I'm again not going to explain it in detail. If you want to know, there's a very nice paper we did a couple of years ago. So suppose you're 2 Egyptians and you have to build a pyramid. Would you, this is again a physics quiz, just to wake you up, would you pile the stones, pile the stones and drag with 2 people? Would you each drag a stone? That's answer B. And answer C is it doesn't matter. So, who says answer A? A couple of people. Who says answer B? That's a couple of people. And who says answer C? That's the vast majority. You're all wrong. You should read our paper. Well, so the solution is complicated, and that will become important in what follows. Basically, any friction engineer and most of you say that it doesn't matter because you can look up in tables the friction coefficient of steel on steel without having to specify anything about the shape, the weight or anything. Yeah, and so that means that it really doesn't matter. If you actually do the experiment, you'll find that most of the times it does matter, but that is not relevant for engineering purposes, fortunately, because otherwise we couldn't do friction engineering. And so the first friction engineer some time ago was Da Vinci, who already concluded that answer C is the correct one. What he did is he slid wooden blocks on wooden planks, and he concluded that however he put the block, you could imagine that if you put the block on its side, the area with which you slide is smaller, and so it should be easier. But Da Vinci already found experimentally that that is not the case. And even more so, he said that the normal and the friction force, so the normal force is here just the weight of the object, and the friction force is the force you need to pull it, have a constant ratio of 1/4. And that was the gospel until very long. And one never found the 1/4 again. But this is really the ballpark of what friction mechanics can do. Yeah, and so any friction engineer that tells you he can do better than Da Vinci is probably lying to you. Now, because oh, so you have because friction is so important, it is very important to understand systems that have a very low friction, such as ice skating. Yeah, so I will show you measurements, and there are many more measurements that the friction of a skate on ice the coefficient of friction on ice is an order of magnitude smaller than the measurements of Da Vinci. So I will skip the movie because you know how ice skating goes. Yeah, so the table, I'm not gonna try again. I try to learn from my mistakes. The table was the number of gold medals in the Winter Olympics. And at some point they started out with the skating, and for a very long time Holland was on top of the medal list, I think. Later on they went down a little bit. And our friend Howard Stone investigated also how the Chinese already knew that the friction on ice was very low. So there's a 300-ton piece of stone that was transported by the Chinese to the Forbidden City, 70 kilometers further from the quarry on ice roads. Yeah, so this has lots of practical applications if you want to build a Forbidden City or something like that. And as I told you yesterday, I had sworn to myself never to do anything on water or ice because the community is too complicated. And part of the community is my brother, Misha, and at some point Misha published a paper that said, yeah, there is pre-melting or surface melting, and it happens already at -70, that the first bilayer of ice melts, and then at -20 there's another bilayer of ice that melts. And I was like, yes, I have a setup for doing friction experiments, and if the gospel that the friction is low of water on ice, because of skate on ice is low because there's a layer of water, there should be an abrupt change at these temperatures. And so that's what I sat down to do. And then we got a whole soccer team involved. This is also the politics of the water community. You have to include everybody. But it's my brother and me and some people from Amsterdam. And the main culprits here are my partner in crime in friction, Bart Weber, and a PhD student, Rinse Lieverink. Yeah, and so the lovely picture you have seen. And so, this I said to you yesterday. I need to clear up one confusion. There's people that think, I got asked over both dinner and lunch, that there's no ice 1H below -22 degrees C. That's not true if you look at the phase diagram. What happens is that if you increase the pressure, you can no longer transform it into water at -22 degrees. Yeah, so there is ice 1H, but below -22, you would transform it into another form of ice and not into water. And so if the ice skating story is true, the water layer ice skating story, that shouldn't be possible. So that was my remark. The remark was not, there's no ice 1H below -22. And so pre-melting we have discussed and we will discuss. This is a very interesting one, curling. What actually happens when these people are frictioning with the room. Is that frictional heating? Perhaps. I don't know, but we bought a very special curling pad, so the broom that they use actually cost a couple of $100. And so we have this pad, and we're trying to rub it over the ice to see what happens, because I have no idea what these people are doing, physics-wise. Sorry? You pebble your ice. I heard that story, yeah, but you think you simply you smooth it? I would guess that if you have just a couple of points of contact, that the friction would actually be lower, and Da Vinci actually says that it doesn't matter. But I'll come back to exactly that point. Okay, so the experiment is deceptively simple. I have a rheometer, and it's actually only a rheometer head. And normally what you do, if you have a rheometer, you put a liquid between the rheometer plate and a bottom plate, and then you shear, and you measure the torque with which you need to shear at a certain speed, and that gives you the viscosity of the liquid. And if you buy a very fancy rheometer, it actually also measures the thrust that the liquid, if it's a complex liquid, might exert onto the top plate, and that is called the normal force. Yeah, and so this is a variation on the rheometer theme, where instead of a bottom plate, I use a layer of ice, and instead of a top plate, I actually glue a steel sphere onto the plate at a known distance, and then I drag the steel sphere over the surface. And the nice thing of the rheometer is that it spans many orders of magnitude in speed and in force. And so what I end up with, if I measure the torque, I can deduce the frictional force, the force necessary to drag my sphere over the ice, and the rheometer immediately gives me the normal force, because it has a normal force transducer on the axis of the upper tool. Yeah, and so this is a friction machine, and it's a very cheap friction machine, because I already had it at the lab, and the importance is it's a very sensitive friction machine. And so I set out to measure the friction of the steel sphere on ice at very low temperatures, because my brother said something very interesting should happen. Yeah, and so this is the actual experiment. We film it here, so there's a layer of sort of ice crystals that have nucleated on the surface, but normally we close everything off, and we do that under a very low humidity, and then we have very nice ice. And so, ta-da, yes? Actually, you will see we just displace the rheometer, which is easier. And so this is the big moment. Will you all pay attention? This is the friction coefficient of our little steel sphere on ice. And this looks terribly complicated. Yeah, so friction is only low at roughly ice skating temperatures. But then when you go to very low temperature, it actually is larger than the friction of wood on wood, which was 1/4 as reported by Da Vinci. And then if you come close to melting, the friction goes up again. So this is non-monotonic, and this is what we need to understand, to try and understand in any case. So this is going to be fun. This happens every 5 minutes. So I was here. It's maybe every time I have a movie. And so this doesn't really depend on the way we make the ice, because that was also a large discussion in the literature. We can make, I can make polycrystalline ice because that's very easy. My brother can make monocrystalline ice because that's very complicated, but if we do the experiment, they give the exact same results. And we can also make ice from heavy water, and that gives something very similar, only the melting point of heavy water is slightly higher than 0 degrees. Yeah, so this is a robust result, yes. Yeah, so we have two setups. We have a Peltier that will cool the bottom, and that is very nice if you're in this region. But if you really want to go low, we use liquid nitrogen, and so we have a closed system with the rheometer axis going in, with liquid nitrogen flowing through a metal plate at the bottom of which we make a metal cup, sorry, at the bottom of which we make the ice. Yeah, and so there's a region where you will fall, but if it's too close to 0, you will actually not fall. And that I think we all know, and that's going to come back in the measurements. Again, it's not lubrication. I showed you the Strybeck curve. These are values as a function of velocity, and as I said, it's easy to do 1, 2, 3, 4, 5 orders of magnitude in velocity, and we find no dependence of the friction coefficient on the velocity. Then there's a dependence, of course, on temperature. Yeah, but this indicates again that what we're looking at is solid on solid friction and not some kind of weird lubrication. At very low temperatures, it becomes complicated, and I will come back to that at the end of my talk. But I showed you yesterday the friction on high-density polyethylene because it had a very similar, it has very similar mechanical properties to ice, and you see that even if you add water there, the friction of the skate on ice is actually much, much lower. Yeah, so this is really an exceptionally low friction system. And so the question now is, what happens? And we can infer a lot of things from just looking at the ice surface. So if we're at very low temperatures and we do the experiment and we look at the ice, it is as if nothing has happened. If we are very close to melting, we actually make a track in the ice. The ice has become so soft that we actually leave a trace of the little particle, which is my ice skate. And this is what I told you. If we want to do a new experiment, we simply displace the rheometer by a couple of millimeters. Now, what is plotted here is the friction force as a function of the normal force, and that also looks complicated. Yeah, Da Vinci, Amontons, Coulomb, they all say, well, the friction coefficient is the ratio of the friction force to the normal force. And so if that is the case, my friction force against normal force needs to be a straight line. And it is at -2, but if we're too close to 0 degrees, it does something weird. The friction force goes as the normal force to the power 3/2, sorry. And if we're too cold, it also does something weird. It does 2/3. The 2/3, you've all learned in undergraduate physics, is simply the Hertz contact. Yeah, so this is just an elastic deformation of the sphere surface on the ice. this is what I would hope that would happen every time I do a friction experiment. And this seems to be new, and it seems to be related to the fact that we make a trace. And we go from elastic to plastic. So let's first do the plastic part, because it's actually the easiest. What we have is a sphere that is actually moving through part of the material. Yeah, and then the penetration force, the normal force, is given by the penetration hardness of the ice, the limit at which the ice starts to deform plastically, times this area. And this area I can, of course, transform into a contact radius, and there's the radius of the sphere. And then the normal force is simply the penetration hardness divided by the normal force is the contact area times the plastic deformation limit, the penetration hardness of the ice. Yeah, so that is an easy calculation. We can measure the penetration hardness. Sorry, did I forget something? Ooh. No, it was not a movie. Maybe I should restart my computer. Let's see if we can make it to a break. Yeah, and then what I forgot to say, this is what we call the plowing force, which is the force that I need to drag the sphere through the material, and that is the contact area times the penetration hardness. Yeah, that's a simple mechanics calculation. Yeah, and so if we know what the penetration hardness is, we can calculate the friction force. And the penetration hardness is something you can measure. We do it in two ways. We push a sphere into the ice, or we push a cone into the ice. It doesn't really matter how we do that, but it gives us the dependence of the penetration hardness on the temperature. And then what you see is that at very low temperatures, the penetration hardness is really very large, much larger than the force per unit area that you exert on the ice. And so here I would expect no contribution of the plowing friction to the overall friction. But here it becomes very, very small, and this is where we see the traces. And then the friction coefficient will go up because you are plowing through the ice. And that is something we can actually directly compare to the data. So this is the plowing friction calculation without any adjustable parameters from the penetration hardness measurements, and you see that it gives a very good description of the data close to the melting temperature. Okay, we understood something. Yeah, and this is the reason why if you're walking over snow close to the freezing temperature, you won't actually slip. Yeah, you will simply... Right, right. Yeah, just as the little sphere does, as you see here. And so, what happens then at low temperature? Well, if I cut off the part where we see the plowing, we actually get a very steep dependence of the friction coefficient on temperature. That is completely continuous. That seems to be exponential in the inverse of the temperature. So this suggests an Arrhenius process. And I earned a beer because at the 2 magical temperatures of my brother, nothing serious happens. Yeah, so the hope was that there would be some discontinuity, and apparently what happens at the surface has no effect on the friction whatsoever. Yeah, so this is the summary of what these 2 errors are. These 2 arrows are, that's the magical temperature of the MNOS paper. And so the question is, of course, what is the activated process? And so I dove into the literature, and there's, of course, lots and lots and lots of things already known about ice. And there's an MIT professor of ceramics who was very interested in sintering, because making a ceramic material is sintering 2 solid materials without any liquid being present into a continuous film. Yeah, and so that actually looks like ice sintering, and he must have had the same idea, because he redid the Faraday experiment, who had these 2 ice cubes that he brought together. He redid that in a controlled way. He had 2 ice spheres in a freezer. He brought them into contact, and then magically the neck between the 2 spheres began to grow. Yeah, and that allows you to quantify the qualitative remarks of Faraday. And so the result is very interesting, because he also says that there need not be any liquid. Yeah, he says the welding together of ice particles is a result of surface diffusion. Yeah, so things can diffuse simply from the boundary towards the neck. And so he has some data, not a lot of data, that actually substantiates that mechanism. So this is very nice, because it goes with everything that I've told you so far. The only problem is that if he tries to get the activation energy from his surface diffusion measurement at different temperatures, yeah, so it's hard for you to read probably, but at low temperatures it actually goes much slower, the neck growth, than at high temperatures. So this is radius as a function of time. And so if you plot the rate as a function of the inverse temperature, you get the activation energy. And the problem is that this activation energy was actually more than a factor of 2, almost a factor of 3 different from what you would expect for surface diffusion. Nonetheless, this is a quantitative experiment that says there's no need for a water layer for transport to happen. Yeah, we've been discussing over and over again, if we want transport to happen in ice, we need ice to transform in a liquid before it can be transported somewhere. And this is proof that one doesn't need to do that. And so at that point we did a little simulation together with the group of my brother of the mobility of the ice molecules on the surface of ice, and we see a direct correlation between the mobility, here expressed as the inverse of the mean square displacement per unit time, and this Arrhenius friction coefficient. Yeah, but again, the diffusion coefficient in the simulations is not exactly that that you would need for simple surface diffusion. Yeah, and so I think the million-dollar question is now, okay, it appears that stuff can move on the surface of ice, but what is actually the mechanism? Yeah, so intermediate conclusion. Oh, I'm not in presentation mode. Why don't you say something? Ah, I don't think it helps. So ice is not slippery because of a water layer, but rather due to a mobile layer of molecules at the surface. And the way I imagine that is suppose that I would put little ball-bearing balls all over the floor here. It would make the floor incredibly slippery. So if this is a 2D gas, if the ball bearings would move with Brownian motion, you would actually have difficulty squeezing them out from a contact, and it would make the floor even more slippery. And so the important conclusion for ice skating is there's two regimes. There seems to be an Arrhenius regime, where we are still looking for what the activated process is, and a plowing regime, and there's an optimum ice skating temperature of -7 degrees C. And then you, of course, ask, what do you, of course, ask? Exactly, what is the ice temperature for the Olympic skating ring? And if you look that up, it's between -5 and -9 is the optimum temperature. And they know that there's an optimum temperature, simply from looking at the times that the skaters make. But now we actually understand why that is. Yes? Yes, and that's after the break. Stay tuned. No, slower. Yeah, so it's Arrhenius. It's an activated process, and so it increases very much when you increase the temperature, exponentially fast. Let's go on. So I will answer your question. But not before coming back to Faraday, because what Faraday said is, I can put those two ice cubes together, and this will work at relatively high temperatures, but it will no longer work at low temperatures. Yeah, and I think that is in perfect agreement with the fact that this is an Arrhenius process, where the rates decrease exponentially with decreasing temperature. You would simply need a lot of time, a lot of time for two ice cubes to sinter at very low temperatures. Yeah, so I think this also explains the observations of Faraday. But the million-dollar question is, of course, what is the dynamics of the molecules at the surface of ice? Yeah, that's the question that we really want to answer. And together with Menno, who's still awake, that's good, we actually found a very cute way of doing that, if I say so myself. Yeah, so this is what the ice surface could look like. There may be a little bit of roughness, and there may be a little bit of disorder close to the surface. But what would happen if we would cut it? If the two ice spheres of Kingery sinter, this scratch would probably fill up. And the way that it fills up would probably tell us what the mechanism is. Yeah, that's what we're going to do. So the question is ice a self-healing material? And the answer is yes, ice is a self-healing material. This is one of the first observations. And so what you see here is a scratch that we made in the ice. These are grain boundaries, so our ice is not very pretty. But the scratch, we can measure with a profilometer how deep it is. And then we simply leave it with its equilibrium relative humidity. And magically, the scratch heals. Yes? Sorry? Because they always are. But yeah, I will show you a better movie. This was the first movie. Okay, so the black thing disappears. The black thing is a scratch. And so, sorry? No. Yeah. And so this is the quantitative measurement. you see that we had this dent here, and so this is a cut through the scratch, and you see that indeed the scratch heals, and the surface is really, 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 really flat. Yeah, which helps with my explanation of the little ball-bearing balls, because if the surface was rougher than the size of the ball-bearing balls, this wouldn't work. For this, I will show you in a second. But first, the hard work of Menno, because we wanted to do this quantitatively under the profilometer. This is an optical confocal profilometer, and it basically scans through the surface and looks at the changes in reflection, and then transforms that into a depth profile. That's why it's called a profilometer. But you need to do that at controlled humidity, so we put the whole thing in a box, and then in the box is a cooling plate, a layer of ice, a very largely magnifying objective, and Menno, who's not in the box. I've tried convincing him to be in the box, but he doesn't want to. With a very thin razor blade, he makes these scratches. And so this is the better measurement. Where you can see quantitatively the surface with the scratch. You can see the scratch before and after disappearing, and quantitatively you can average over this direction, and then you get an average profile. All right, does this help? Well, we think it does. Yes. That's exactly what I'm going to do. Exactly. Bear with me for another 5 minutes. So if we have these spheres that sinter, or my little scratch that heals, there can be different mechanisms for the transport. There can be water, a water layer, a pre-melted layer that flows simply under the action of the surface tension into the gap, and that then freezes and makes the neck grow. The second possible transport mechanism is that ice molecules evaporate and redeposit there where they are happier, namely in the gap or the crack. It would be possible in principle to have matter arriving from the bulk and going to the surface, and then the fourth possible mechanism is molecules diffusing over the surface and having a higher probability of sticking here than remaining over there. And so the nice thing of this experiment is that we can make that quantitative. And Mullins in the 1960s actually wrote down a single differential equation. So this is for a single sinusoidal perturbation of your surface. And he says that the amplitude change in time is some temperature-dependent prefactor times 2 pi over the wavelength of the amplitude to a power n times the displacement itself. Yeah, so this single equation actually describes all the 4 processes that I mentioned to you, because if n is 1, we get fluid flow. If n is 2, we get sublimation condensation. If n equals 3, we get volume diffusion, and if n equals 4, we get surface diffusion. Yeah, and so all we need to do is to transform this series of profiles at different times. So here now you have the time. This whole crack healing process is not yet completed after something like 3 hours. So Menno is a very patient guy, or has a lot of time to drink coffee, I'm not sure. Right. And so what we do is we write down the equation. We, we describe the profile as a Fourier sum, and for each of the Fourier sum, we can do this, for each of the Fourier components, we can do this calculation and then see whether n equals 1, 2, 3, or 4 is the winner. And so these are, so what we do is for n is 1, 2, 3, 4, we start out with the initial profile, because that's our initial condition, and then we simply evolve the solution in time with the n that we want. And if we do so, we have a very clear winner, which is evaporation condensation, and that you can see here. So here you have the initial profile, which is perfectly described by the model because it's the input of the model. But then if we look at the time evolution, we see that the n equals 2 solution actually does really well. And then we can compare the different models to the data. And so viscous flow is this one, sublimation condensation is this one, volume diffusion is this one, and surface diffusion is this one. Yeah, so you will agree with me that the mechanism of crack healing here is evaporation condensation. The problem with if you increase the relative humidity is that you will get the ice growth everywhere on the surface. Yeah, and so you don't have a neat experiment anymore because your base surface will translate and become very rough. So that's why we prefer to do this as close to the equilibrium relative humidity as we can. In vacuum, you mean? Okay, so I will show you at the end of my talk that if you are close to vacuum conditions, the whole thing will sublimate really rapidly. So that's also not really an option. Okay, then we were left with the puzzle of the activation energy. From our crack healing measurements, we get some effective diffusion coefficient of ice through the air. This is not the diffusion coefficient of ice molecules on the surface. As a function of the inverse temperature, yeah, we can do this at different temperatures, and we get a very nice Arrhenius behavior. Yeah, so I'm very happy, because I think this is what causes the high mobility of ice molecules on the surface of ice. Yeah, and I'm not now sure it's ice molecules on the surface of ice, because n equals 1 was liquid water, and it didn't work. Yes. Yeah. Yeah, I don't think the different facets are very different. But if you've looked at the movie, if you will bear with me and hope that my computer doesn't crash. So you see, these are different crystallites, and they probably have a different orientation. And so this is a scan through all of this, and we don't see any significant differences. Yeah. Okay, so sublimation condensation gives an activation energy, and the activation energy is something like 58 kilojoules per mole. And so if you look at the sublimation activation energy, because the condensation is actually energetically more easy, you find 55. Yeah, and so we are really convinced that this is the mechanism behind the mobility of ice molecules on the surface of ice. If we go back to the strange activation energy that Kingery found, we can actually force fit the surface diffusion model onto our data, and then we get another activation energy, and then we actually get the exact or almost the exact same value for the activation energy that Kingery got, which was not surface diffusion. Yeah, so we think that if Kingery had gone to lower temperatures, as we did, and did more measurements, he would actually have agreed with us. And so the conclusion is local sublimation and condensation. Which is this? Thanks, Menno. And so the very important conclusion is that if you have an ice skating rink, that you don't need to buy all these fancy machines, you just have to wait. Right? Many hours. Yeah, okay, but so before the night you don't need to do it. And we should go to. We have an ice skating rink close to the university, so we will try and convince them to not do this and see whether it changes. There was a question. Yeah, just flushing nitrogen at a certain rate, and then looking at the relative humidity, and we know what the equilibrium relative humidity is at a given temperature. Okay, I think it's time for a little break. After the break, stay tuned. All right. So with apologies for the mess with my computer, I'll buy a new computer. And so I would like to pick up where my computer quit on me yesterday. I had tried to convince you that ice skating had something to do with an activated process, and then that activated process might be evaporation, condensation of ice molecules at the surface of ice, and there's no necessity for a liquid at the surface to have any transport. Yeah, solids have all kinds of transports at their surface. And so I started out my friction measurements because my brother said there was a liquid-like layer appearing, a liquid-like bilayer appearing at -70, and then at -20 there was a second bilayer that melted. And so I was wondering whether that could have something to do with the friction, and the answer was no, nothing particularly exciting happens at -70 and at -20. And so I tried to understand what my brother did, and I'm going to try and explain it to you. So this is the famous paper, bilayer by bilayer surface melting of crystalline ice. So this is really very clear. And so the drawing that they have is that at very low temperatures the ice surface is pristine and everything ends in a nice crystal. And then at -70 there's the first bilayer that melts and that makes something a bit more messy. And then at -20 there's another bilayer that melts and that makes for something that is a bit messy. And they conclude that from very fancy spectroscopy techniques that are basically a sort of infrared spectroscopy, but very specific to the surface because they probe a transition that you can only see if the symmetry is broken, i.e. at a surface. And so this is a typical infrared spectrum, and what you see is a typical infrared spectrum, which is what in French one would call a patate, a potato. But there's all kinds of profound things in this series of potatoes, because you see that when the temperature increases, there's a slight shift to the right, which they call a blue shift. And they can do this in an experiment, and they can do this in a simulation, and that they can probe a peak that they say is the free OH. And so when my brother gives a talk, he says, I'm a water molecule, yeah, and so my body is the oxygen, and the hydrogens are my hands, and so infrared spectroscopy basically measures this vibration. Yeah, that vibration depends on the environment, and so you can think of that measuring the dynamics of the OH at the surface. And so the conclusion is that there's two kinds of hydrogen-bonded water molecules at the surface of ice. One is called DAA, and it has 3 letters because it has 3 hydrogen bonds, and so it's very strongly bonded to the surface. And then there's DA, which only has 2 hydrogen bonds, and so that is less strongly bonded to the surface. And the blue shift, the shift to the right, simply means that more of these molecules get transformed into more of those molecules. Yeah, and so you would expect that the surface becomes more mobile. And so this is the amount of mobile and immobile molecules, and you see that if you go towards the melting temperature, the number of mobile molecules increases. Yeah, and so for me, what they see is a completely continuous transition from very immobile molecules at the surface of ice to very mobile surface molecules at the surface of ice, and I see no reason to assume a discontinuity. And if my brother and I agree on that, we're reconciled with each other, because we're both simply saying that the dynamics of molecules at the surface becomes much faster. I'm not sure he agrees. I'll show him this video. Yeah, but this reconciles me with my brother, but I don't know whether it reconciles my brother with me. Now, getting back to the ice skating, there's a question that you haven't asked me. Yeah, because what I've been arguing here is everything has to do with the mobilities of the ice molecules at the surface of ice. But what about the counter surface? Yeah, these are not free molecules. These are actually molecules that are in between ice and my ice skate. And this is actually what you see turning here on my rheometer on the ice is a piece of a real ice skate. Yeah, and so the question is what I've told you before the poster break yesterday. Is there a way? Oh no. Oh no. So I have a triple backup. No panic. All will be. Yeah, so I say. Yes, I should plug it in. Let me do that. And so the question, so there's some people here that are part of the French effort of trying to improve the physics behind sports in France. So I'm trying to improve the physics behind skating in the Netherlands. And so the question is, what is the best ice skate? And so if you think about it, if my simple skate is a small sphere and I put some normal force on it, it will plow much deeper than if I put that normal force on a much bigger sphere. Yeah, simply because the amount of plowing is due, as I told you, to the penetration hardness of the ice. Yeah, and so that also means that if I look at the friction as a function of temperature, that the large sphere actually starts to increase much closer to melting than does the small sphere. Yeah, that makes a lot of sense. And then it also makes a lot of sense what people do to real ice skates, because if you read up on that, there's a magical radius of curvature for ice skates that is, wild guess, anybody? 23 meters. And so the thing you see here is actually a very small bit of that radius of curvature of 23 meters, and the rest we removed. I'm not going to play this for a long time. But lo and behold, if you do this, you see that the point at which the skate starts plowing is actually even at higher temperatures than the larger sphere. And so this makes a lot of sense because you simply need to avoid the plowing to go fast on the ice. Yep. So I'm gonna do something different. I'm gonna do this in Keynote. And I transformed the PowerPoint into Keynote, and there's a few small problems. Okay, and so to really understand that, we really need to think a bit deeper about friction. And I told you yesterday that Da Vinci did experiments where he had wooden blocks and a wooden plate, and he concluded that it didn't matter whether he put the block on the side or on its flat face, that the friction coefficient was always the same. And so the friction coefficient that Da Vinci measured and that many engineers measure every day seems to be independent of the macroscopic contact area between the two surfaces. And that seems a very strange observation, but not if you realize that all surfaces are rough. And so if you zoom in on the contact, you will see that only a very small fraction of the two surfaces actually touch each other. And so Amontons proposed that it could be that if I push twice as hard on this microscopic contact, that I might make twice as much surface. And then if, and only if, the friction force is proportional to that area of real contact, the contact area drops out of the friction coefficient. And then we have an explanation for Da Vinci's measurement, but also for the everyday engineering observation that you don't need to specify the shape or even the surface properties of two sliding objects to get a friction coefficient. The friction coefficient of wood on wood is 0.4. It's actually not 0.25, but that's another story. The friction coefficient of steel on steel is 0.3. Yeah, and that's very useful for engineering, and it all bears down to believing Amonton's law. Yeah, and so for a physicist, this is perhaps not completely obvious, because the physics is actually very complicated, but for engineers this actually works. So how to... Ooh. Holy ships. Even slower? Yeah. No, I don't want this. I don't want this. Oh yeah, I do want this. So, if you buy a new pair of ice skates, they're actually very nicely polished. And this turns out to be very important because the roughness of the surfaces, as I just told you, also does something. And what the roughness does, yeah, is it makes, if you are very rough, you have a smaller contact surface, and that means that you have a higher pressure and you get more plowing. Yeah, and so if I take my piece of skate or my skate model, which is a little sphere, and I measure the friction force as a function of the normal force for different roughnesses, I actually find that what everybody knows, the rougher the surface, the higher the friction coefficient. Yeah, and so what happens if my skate isn't well polished is that I start plowing much earlier, and I really don't want that. Yeah, and so I should compare really the real pressure on the contact to the penetration hardness of the ice to decide about the friction coefficient. However, that means that I need to measure or infer somehow the pressure, and that's not an easy thing because these roughnesses are terribly complicated. But I can measure them, and so what we typically do is we have the spheres, we can roughen them, we shake them in a little container with a bit of sandpaper, for instance, and then we have this profilometer that allows us to get a roughness map. We subtract the curvature of the sphere, and then what we end up with is a measure of the roughness of my surface, or even a complete map of the roughness of my surface. And then I can do a finite element calculation, which is the standard thing that people do in friction mechanics. I put in the measured surface roughness. I assume that my counter surface is flat, and then from the roughness map I can get the real contact area between the two surfaces for a given normal force. Yeah, and if I have the real contact area for a given normal force, I can calculate the pressure and then compare it to the penetration hardness. And this is, to make a very long story short, the result of a lot of measurements at different temperatures and at different surface roughnesses, and also for 3 or 4 different types of material. Yeah, and so what I told you before the long break was that I thought that the friction force was proportional to some Arrhenius factor. Yeah, and the Arrhenius factor has to do with the mobility of molecules at the surface. What happens now if I press on the surface is that I will hinder the mobility of these molecules, and I have to correct for that. And A.Huerre, who dropped off my slide, proposed that that is actually a correction to the activation energy. Yeah, so my activation energy gives the difficulty or easiness for the molecules to move. And if I confine them, I actually increase this activation energy to an effective interaction energy. And so here we say that this exponential factor is actually proportional to the real pressure over the penetration hardness, because that gives the difficulty with which the molecules can move. And so if I then plot my measured shear stress, so the friction force basically per unit area, as a function of the contact pressure that I now have inferred from my finite element calculations, I actually get a very nice agreement. Yeah, and so skating is really given by the mobility of the molecules at the surface, but if I press hard enough with a counter surface, I actually hamper that mobility and skating gets more difficult. Eyring also predicted how the friction would then depend on velocity, and I showed you previously these data at -90 that we really didn't understand because it didn't seem like solid-on-solid friction, and it wasn't lubrication either. But if you take the confinement effect of the counter surface into account, you basically predict that there's a logarithmic dependence on the speed, and that is really well borne out in the data for -90. And it's a bit less good at higher temperatures because especially for rough surfaces we have a lot of plowing there, and so the quantitative comparison is actually a little bit more difficult. So I would say it's in rough agreement. Yes. So the manufacturer says the resolution is about 10 nanometers. So lateral is optical. So that's half the wavelength of the light. It's like 200 nanometers. But the important one is the Z resolution. The manufacturer says 10 nanometers. We actually calibrated our profilometer with an AFM, and I would say it works really well up to 50 nanometers, but not below. Then you really have to do AFM. And so this was my remark about roughness is always complicated because roughness is always a power law behavior in the length scale. So this is really a big mess because in order to fully characterize your surfaces, you need to measure all scales. Anyways, we now understand friction, so I want to conclude this part with trying to convince you that there's something very easy that is different between ice and all other materials, and that's of course the mobility of the molecules at the surface. Yeah, so I look at my car every day, and the scratch that my wife made never disappears. She did. You can ask her. And so if I look at the ice surface, I look at it for an hour or two, and the scratch actually disappears. To bring this point further home, this is Denver on a day that it snowed. And this is a day later. And what you see is very important because all the snow, or almost all the snow, has sublimated. But the rest, the buildings and the trees and the grass and everything else, hasn't sublimated. Yeah, and so this clearly demonstrates the difference between ice and all other solids. Yeah, and I think that part of the confusion of the liquid layer that has to be there finds its origin in this large difference. We don't have the habit of considering that solids evaporate. To show you that this is actually the case, I'll show you another experiment of Etienne, where we have an undercooled water droplet that starts to evaporate. We measure its volume as a function of time, But since it's undercooled, at some point it will freeze, and it will continue to evaporate. And if you do the experiment quantitatively, you see that the rate of evaporation is actually identical. Because it's not the difficulty with which the molecules leave the water of the ice that is the limiting factor, but the transport of the molecules through the vapor. Yeah, you have saturated vapor pressure above the drop, and you've imposed a certain vapor pressure at infinity, and so what limits the evaporation of any drop, and so also a solid ice drop, is the transport through the vapor and not the difficulty of molecules to leave from the solid or the liquid. And so as a tribute to the previous speaker, oops, did it disappear? It didn't disappear. This is an experiment of Kenneth that he sent me, and it's a beautiful snowflake that grows without any defect. And it's really very pretty, but what he hasn't shown you so I think this breathing is controlling the relative humidity, right, Kenneth? Yeah. So when it has grown, he gets rid of the relative humidity. And then it very rapidly disappears. Yeah, and so the conclusion is ice is different from all other solids in that it has a high vapor pressure. That makes for very mobile molecules at the surface, and those mobile molecules you can try and use to quantitatively understand ice skating, self-healing, and perhaps a number of other problems that you want to think about with ice. Exactly. No, so for me mobile means, you can grab molecules from the vapor or you can grab them from the surface, it doesn't matter. The self-healing experiments seem to suggest that you're more likely to get them from the vapor. But so if you have a faceted surface, the thing we were discussing before the coffee break, I think the facets can disappear. Yeah, and so that's also suggested, I think, by the beautiful movie of Kenneth. The facets can disappear simply because the molecules leave and then reattach elsewhere. And I think this is also what people call the aging of snow. Kenneth, do you agree? So old snow has a very different morphology than young snow, and I think the transport through the vapor is an important aspect of that. And there's one poster that seems to suggest exactly the same thing here. Yes. Kenneth? I'm so glad you're here. So, no, this is all very slow. Yes. Yep.
Is it that with other materials that topology changes of that diagram, or just that the triple point gets moved to some extreme
So the topological change is that the liquidus for water and ice has a negative slope, and for almost all other materials has a positive slope.
I'm asking, would another material, I don't know, this big silicon, would it no longer have a triple point, or does the triple point get moved to some extreme part of the phase diagram?
So I think water is the exception. So if you try to map the phase diagram of water on argon, for instance, yeah, something simple, then water is further off than if you would try to do that with iron or silicon. Yeah, and so everybody attributes that to the hydrogen bonding, but I don't know what hydrogen bonding is, except for a dipolar interaction. No, I don't think dry ice is special. In what sense? Yes, but it's much, yeah, but it's much further. It sublimates very rapidly because it's much further from its coexistence than the snow in Denver, basically. Yeah. All right, then I'll change gears. And I'll try my second presentation. I'm not sure I have the last one on Keynote, so I'm gonna try PowerPoint. It doesn't have much movies. Okay. So as with each subject, I start with a picture of a movie of something that I won't explain to you. But at least I will partly explain this to you. Things that are outside deteriorate. We are all used to that. And Nushin in our group has a whole research line on trying to better understand the degradation of materials outside, and she very specifically works with musea like the Rijksmuseum, who have all kinds of artifacts that have been damaged, and most of the damage occurs actually by crystallization. And there's two types of crystallization. They can either be salt in the material, and so if it rains, the salt gets dissolved, and then if the water evaporates, the salt gets transported and can crystallize somewhere else. And that can lead to all kinds of damage or ugly white stains on your building or artwork. And the second, and that's of course what I want to talk to you about today, is ice crystallization. Yeah, but you should keep in mind that this is mostly the work done by Nushin and her team. But she allowed me to tell it to you. And so we had a master student, Rosa, who did a lot of work on ice crystallization and mechanical damage, trying to really understand what happens at the pore scale. Yeah, and so what you should realize is that roads and statues of lions are actually porous materials, like the sponge here, and as soon as there's water somewhere from rain, or it can be groundwater that also transports some salts, they will suck up the water, and then if the relative humidity changes, salts may crystallize, and if the temperature changes, the water may freeze. Yeah, and so we all think, well, yeah, we've done the experiment of the white wine bottle in the freezer, and so all damage is due to the fact that water expands when it freezes, and that will break your material. As Menno shows, it's a bit more complicated than that. But if you think about porous materials, that especially porous materials that are not completely saturated, and that is of course the case when you think about a road or the statue of a lion or any other building, it seems easier for the liquid to crystallize in a direction where there's vapor than to actually try and exert a pressure on the material. Yeah, so it might exert a pressure, but I really don't know yet how that works. What I do know is that stones actually break at saturations far below 91%. Yeah, and so if you believe in the ice expansion story, you should really try to come up with a plausible way of explaining that, especially since these porous networks do not really confine water in all directions. Yeah, and so the simple question we asked is what happens really at the micro scale. Benno has shown you what happens at the macro scale, but because it's very pretty, I will show it to you again. Yeah, so this is a vial in a freezer, and then because there's large gradients, because it's a microscopic centimeter size sample, it freezes first close to the walls, and then you have a liquid pocket, and when that liquid pocket freezes, it expands, and then the vial breaks. Yeah, but this is not at all probably what happens in a porous medium. Yeah, and so the question whether a growing crystal can actually exert a pressure is a very old one. So it's been more than a century of debate. And there's very lovely experiments where people have tried to grow salt crystals between two plates, putting a weight on the salt crystal and trying to see whether the growing crystal would actually push up the weight. And the answer is absolutely not trivial. And PowerPoint is absolutely not trivial either. But Becker in 1905 said the weight of a kilogram will actually be lifted up a little bit because of something called the crystallization pressure. And the crystallization pressure is simply the chemical potential difference to coexistence. Yeah, so if you have a supersaturated solution, you could think of think of a crystal in a saturated solution. If you would press on the crystal, you would increase the elastic energy of the crystal. And since you don't increase the energy of the molecules that are dissolved, the crystal will slowly dissolve if you press on them. Yeah, it's a bit the opposite of pressure melting of ice, because the liquid has a different slope. Same thing if you try and grow a crystal between two plates with a weight on it. The maximum force that that crystal could exert is simply given by RT over V log saturation over the saturation concentration, the chemical potential difference distance to coexistence. Yeah, so that's the crystallization pressure, and you can also define a crystallization pressure for ice. However, there's an additional thing that you need to think about or to worry about if you think about this experiment or the ice growth, because if you grow a crystal and the crystal simply bridges the gap between the two glass plates, there's no way in which you can add other molecules into that crystal. Yeah, and so the only way in which you can actually exert a pressure is if there's a liquid layer between the glass and the crystal, that gives you new ions to make the crystal grows. Yeah, and so that was known theoretically, but experimentally, it's actually only very recently that we succeeded in what I think is providing convincing evidence. And so the experiment is practically just as simple as the crystal between two plates. We have a drop of salt water between two rheometer plates. The rheometer still measures the normal force. We let the droplet evaporate. Salt crystal starts to form. This is simple NaCl. And then if we measure the force as a function of time, you see that the moment where the crystal almost fills the gap between the two plates, you all of a sudden get a force. That's really cool, but the question was, is there a layer of water? And so if you look very carefully at the images, you can actually see the layer of water, because the image completely changes at the very end of the evaporation. You see the last layer of water evaporating. What is perhaps more convincing is that you can do a treatment where you make the surfaces hydrophobic. Yeah, they're glass surfaces, so I can do a simple silanization treatment. And so if I have a sodium chloride crystal on a hydrophilic surface where water can easily form a film, I get this large force. But the red curve is a sodium chloride with a hydrophobic surface. We don't see a film and we don't measure a force. Yeah, so this is really cool because it's really evidence that this layer should be there. Now, what about water and ice in a porous medium? Yeah, there's lots of thoughts about what could happen. You could have the water that freezes and then exert the crystallization pressure, provided there is a liquid film. But there's also other effects like cryosuction, transport causing, so there's a there can be transport through the porous media that can also in principle do damage, etc. Yeah, ice lensing. There's of course the effect of thermal expansion of the ice. If you bring ice from -10 to -5, it will expand, and that could also lead to damage. And so the question is, what really happens? Yeah, and so what we did is we made a very simple cartoon experiment of a part of a porous medium. Yeah, and so we do a single pour and we go and look at what happens. From what I told you previously, we can already anticipate that there is a liquid film. Yeah, so I told you, if I do the calculation of the Hamaker constant, giving the interaction between surfaces 2 and 1 with a layer of medium 3 in between, I can have either sign. I can have an effective disjoining pressure that tends to approach the two surfaces, and then I won't get a film, and I can have an effective disjoining pressure that tends to separate the two surfaces. And then of course the phase number 3, which is water, will come in between. Yeah, and what I also showed you is that we know the refractive indices and dielectric constants of water and ice. Those of glass, because glass is what we're going to use, we can also use, and this is what I call stone here. And if you do the calculation, you find the Hamaker constant that is negative, and so that tends to separate the two surfaces. And I anticipate that in my pour there will be a wetting film. Cool. So what do? Well, we really want to do a controlled experiment in which we can see and measure everything. So instead of taking a complicated pore, we take a rectangular capillary that we partially fill with water, because the question was what happens if there's only partial saturation. And then we have a very simple cantilever measurement that looks at whether the glass expands or not when we freeze the water. Yeah, so everything is on a Peltier, and we can look at it from the top, and we can see and measure everything. And so what happens is we cool, and at some point it freezes. Then we get a displacement of our cantilever. And then we heat it up again. The cantilever goes back to its initial position, and the ice retransforms into water. And so if you don't believe that the cantilever moves, you can have a very careful look at this movie. But you really have to look very carefully. You see it? Yeah, and so this is everything we need to know, except for the fact that we only have a displacement, and what we really want to have is a pressure. So let me start with the pressure. So we do a very simple, this is difficult to see, but this is a finite element calculation with COMSOL, where we put pressure from the inside to the outside on the capillary and look at what deformation it gives. And that allows us to do a calibration of our displacement. Yeah, and so if we've calibrated our cantilever, we find pressures that are somewhere in between 0.1 to 2.5 megapascal. Yeah, so this is a pressure trace as a function of freezing and thawing cycles. And from the calculation of the chemical potentials, Scherer, some 40 years ago, already calculated that the crystallization pressure, the maximum pressure that the growing crystal could exert, is something like 1.2 megapascal per degree of undercooling. Yeah, we can put compressed air on our capillaries and try to break them and measure the pressure at which they break, and we find that is roughly between 1.5 and 2 megapascals. Okay, and then we cycle, because we know that the more we cycle, the more damage we get. That is something that is known from the field. And so this is the deformation or the pressure as a function of time. And on the right-hand axis, we have the temperature. And so what you see is very surprising. If we lower the temperature, the water freezes. And if we higher the temperature, the water melts again. But what is more interesting is that, yeah, so this is the cantilever reading. When the water freezes, we get a very high peak. Yeah, and this is clearly the expansion of the water when it freezes into ice. But then when we start to heat up, we get a second peak, and this is simply the thermal expansion of the ice. Yeah, so we cycle, and we look at what damage we get. And so, a very long story short. So what you see here, A, B, C, D, is 4 stages of a single cycle. This is the liquid. This is the solid, and what you see is that actually the ice itself breaks, and that makes sense because the ice is actually weaker than the glass. But there's also a break in the glass, and we can identify the breaks in the glass when we remelt the ice, and then this fracture remains. Yeah, so we have two types of fractures. Most of the times these fractures happen when we start freezing. Occasionally they also happen when we heat up the ice due to the thermal expansion. So both are probably important in what gives the damage. And so the further observations, we varied a lot of parameters. We basically only see damage if the contact angle of the water with the wall is high. We have to have very small volumes. If we have very small volumes, we get more damage. And multiple cycles indeed give more damage, as is observed on real materials in the field. Yeah, and so quantitatively, this is what I just said. We get very small capillaries. If they're too small, basically the water won't touch the walls. Small capillaries. Yeah, so if there's too little water, it won't touch the walls, it won't exert any pressure, and nothing really will happen. But if we have too much water, again, we have a very little fracture. And so we think that is because the force is deviated to the side. And the smaller the pore, the larger the pressure. And so that explains some differences that people have seen for different types of porous material. And then the question is, what is the effect of the cycles? And what we actually find is that the contact angle that the liquid makes with the wall of the capillary actually tends to increase with every cycle on average. Yeah, and so what you should realize is that during freezing, the contact line moves, and then during thawing, during melting, the contact line retracts, but the retracting contact angle of water on these capillaries is probably high, and so we get a contact angle that increases with the number of cycles. Yeah, yeah, but it's more complicated than that because there's actually freezing happening in between. Yeah. Yes, yes. So this is really the effect of cycling. At each cycle, we get a higher pressure, and at some point, the capillary breaks, and the experiment is over. Yeah, and so we think that is due to the contact angle evolution. We did a lot of experiments. Rosa did a lot of experiments, and it's a bit noisy, but I hope you will agree with me that when the contact angle increases, the pressure also increases. And so that explains the effect of the cycling. Yes? No, there's nothing funny about. I think this would work for any material. No. So it's not at the end of the warming cycle. Sorry. So what we do is we keep the temperature low for a long time, and then when we start heating up, we get the thermal expansion peak. Yeah? Minus 30. Yeah, so there's a lot of thermal expansion. All right. And so the only thing that is left for us is to try and understand the mechanics of this. And so we did a very simple calculation for simplicity in a cylindrical capillary, where we calculate the stress that the growing ice exerts on the walls. Yeah, you'll have to believe me that this is the correct answer. The evident conclusion is that if there's a contact angle between the ice or the water and the wall, and the ice starts to form, if the contact angle is very high, there will be more pressure on the walls than when the contact angle is very low, because then the pressure will simply be advected to the sides. Yeah, so that's the main result of this calculation that you can see here. So this is the calculated hoop stress as a function of the contact angle. And so not only do we get the right order of magnitude, we see that it increases with increasing contact angle. Yeah, and so we've done a study on a very well-controlled system. But it tells us that it's really a very complicated problem, crystallization in porous media, because we have an optimum in droplet volume. Yeah, so if the pore only has a droplet in it, the droplet will not grow sufficiently to reach the other side, and so that will not cause any pressure. If there's too much, it will simply grow out of the pore. And so what is essential is that surface tension actually confines the liquid to the pore. Yeah, that's also the reason why smaller capillaries break much easier than larger capillaries. And that is the cause of that is that there has to be a contact angle. If it's too flat on the surface, you won't exert any pressure on the wall, and the cycling increases the contact angle, and so increases the damage. As we saw, thanks for the question, it also increases the pressure. The final question before lunch is then, is that even relevant for real stones? And so these are stones. They are pieces of sandstone. I think these are from Fontainebleau. They're either from Fontainebleau or from Prague, and they're about this size. They're 1.5 by 1.5 or 1 by 1 by a couple of centimeters thick, and we can imbibe them with different amounts of liquid, and then we can cycle them. We have two types of sandstone. One is really very hydrophilic, and then if we only partially saturate it, we basically get only films on the grains of sand that are connected to each other to form the sandstone, but we have very small contact angles. We have another type of sandstone that has probably aged somewhat after having been cut, and so the outside seems to be more hydrophilic than the inside, and you can easily see that if you put a drop of water on it. This is the outside. Here you don't see the drop of water, it has completely disappeared into the sandstone. And so the way that the water is in the region between the hydrophilic and hydrophobic part of the sandstone is probably with very large contact angles, and so one would anticipate that these break more easily, right? And lo and behold, we can cycle the hydrophilic sandstone as much as we want. It remains completely intact. In art conservation, hydrophobic treatments are often applied to try and protect the stone statues from the rain. That's a very bad idea, because if you have a hydrophobic exterior and a hydrophilic interior, and that's what happens, we get lots and lots of damage. Yeah, we get micro cracks, but we also get large cracks in the material, and you can easily imagine that if this was the head of the lion that I showed you in the beginning, that the head eventually would fall off. Yeah, and so if you zoom out, you can get this kind of damage, but if you zoom in, if you bring your material to the electron microscope, oh, the arrows actually got displaced. But you can see that even the individual grains can break in two. Yeah, the pressure is so large that you can completely destroy the sandstone. And so without any PowerPoint problems, I've come to my conclusion, well in time for lunch. But so I think that the concept of the crystallization pressure explains most of our observations, but thermal expansion could also play a role in the observed damage in the outdoors. What is important in the porous media is that you have small pores in which there's pockets of liquid, preferably with a contact angle if you want damage. Preferably with a contact angle of 90 degrees, because that exerts a maximum pressure onto the walls because they are confined. Yeah, and so this easily explains what I wanted to explain in the beginning, namely if you have these liquid pockets in porous materials and they do freeze, you don't need to have a saturated porous medium to actually get damage. In fact, we even seem to see that there's an optimum droplet volume fraction, or droplet volume in any case, that would lead to the most damage. Yeah, and so we hope that the art conservation people will actually learn something from what we've done here. And I hope you've learned something from my 3 lectures. Thank you very much.